Yep, there. So I'm going to talk about robots and AI, on-device AI. And, you know, I'm talking about it from both an experience with building lots of robots and as an academic. But why is that not working? This clicker is not clicking. Whoever, can we go to the next one? Yeah, I'm going to need a clicker, so if someone could bring out one that works. Oh, now it works, okay. It's a golden age for robotics deployments, I want to say that. And why is it a golden age? Because AI has driven GPU use. You can put so much computation on board robots that you couldn't before. Commodity hardware is driven by lots of other people. Smartphones give you cheap cameras, tiny GPS chips, tiny inertial measurement units. Electric scooters give you brushless motors up the wazoo. There's an amazing supply chain for motors now that there wasn't 10 years ago. Smart appliances push down embedded processing. And there's 70 years of AI tools that can be harnessed. The new ones have to take a little more care. Now, why do I say this? Oh, and everyone thinks robotic nirvana is about to come. I used to say, everyone thinks jobs will be taken away and we'll all eat grapes and write poetry. But LLMs are probably better at poetry than we are, so we're just going to be left eating grapes. But that's not true. We are going to have to work. It's not going to replace all humans. I've been at this a while. This is in the late 70s. That's me with hair at Stanford Artificial Intelligence Lab in the hand-eye group in 1979. I had done a terrible master's thesis in machine learning in Australia, moved to the United States in 1979, have been on many faculties, have started many AI and robotics companies over time. These are my major commercial robot families that I've built in companies and deployed. And I like to take the logarithm of the number of deployed ones, log base 10. So the Roomba is an 8-digit robot. Tens of millions of them have been sold. So I think about over 50 million now. The PackBot, which is used by the US military and other militaries as a remote operation robot, that's a 5-digit robot, tens of thousands. And then for a while, in the teens, I was building humanoid, human-inspired robots, Baxter on the right, Sawyer on the bottom, and they were 4-digit robots. There's thousands of those out there in factories. And now I'm working on this robot called Carter. I don't have a number of digits next to it yet. We had a little local factory we built in San Carlos for it, and now we're just this week shifting over to Foxconn, and Foxconn is now building it in massive numbers. Over the time as I've built all these robots and deployed them in the real world, all with AI on them, I've developed 3 laws of robotics. You know, Asimov had 3 laws, I got 3 laws. First one is the visual appearance of a robot makes a promise to people around it about how smart it is. And it better be as smart or smarter than its promise, or people are going to be disappointed. So if you build a robot with human-looking hands, it better be as good as human hands, or you're going to be pissed off. So be careful what you promise by your appearance. When robots and people coexist in the same spaces, and for those of you who are out of town, you've been seeing the Waymos, they're robots, they exist in the same space as you, and if they screw up like they were this morning when I was taking an Uber here and blocking me, you get pissed off because you don't have agency over them. You can't tell a Waymo to go over that way, as you can point to a human driver. So you need to, when the robots fail, you need to give humans around agency over the robots. It's really important. Oh, and the Roomba, how did people have agency over the Roomba? It had a handle. If it got caught in amongst cords, you could just go pick it up and move it away. We gave humans agency. And then this is really hard for people in AI to accept. But once you've got a lab demo, at whatever level, you're about 10 years away from deploying that level of demo, not the next 5 years stuff, but that level of a demo for real, in a real deployed robot. And maybe you'll get 99.9% reliability, but that really sucks. That means your robot is failing for over 1 minute per day. That's bad. That gets people really annoyed. Imagine if your car just stopped working as you're driving on the freeway for a minute each day and you didn't know when it was going to happen. You need a lot of nines, but each 9 takes another 10 years, 99.99, 99.999 reliability. And that's different than when there's a human in the loop ready to make correct errors, such as in a coding agent. So these robots look very different. They're purpose-built. The last one, Carter, is for warehouses. And what happens in warehouses right now? People push carts around. So we made our robot look like a cart that people were used to. And they still interact with the robots in the same way. This is our very first deployment. Different model from what we deploy now, but the robots can go sideways. People grab them, people push them. They move around amongst other people. And here's a manual cart. This is the sort of carts you see everywhere in warehouses. So now let's let this play. Do I need to press click? This is in Las Vegas.
Is the most exciting moment for anyone who's been building robots.
Are we going to start again? All the way from the beginning.
Scene 109, take 2.
We believe that robots and people should interact in a way that's positive for people first.
People are so good with their hands, reaching, grasping, picking, putting. We realized we couldn't replace them. What we can do is help them.
Our robot literally has a physical manifestation of what it means to have agency, making the experience for the user as elevated as possible, while creating productivity.
Carter looks like a cart, but it's actually an AI supercomputer. It knows that that's a person, that's a ladder, and it knows how to interact with each of them differently. We want to make technologies that are fantastic to use so that once people have tried them, they never want to be without them.
Our mission is to make robots work for people, not the other way around.
Too much of our technology, we have to adapt to the technology. We're trying to make technology adapt to people. And it looks like a very simple design, but has a massive amount of AI methods on board. And the general architecture, and this is what I'm about to show you for general architecture now, is exactly what Waymos use. It's what our robots use in warehouses. Down the bottom is the world with its physics. The robot has to interact with physics. It's got to pump energy into it. It's got to get energy out of it. It's got to decelerate. It's got to manage its kinetic energy. So there are reactive behaviors and bottom-up perception. That's where the robot touches the world. Above that, there's onboard planners, replanners. Why onboard? Well, in a warehouse, you're often Wi-Fi denied in all sorts of reasons, because there's so much metal in the shelves, you can't get guaranteed Wi-Fi. Likewise, Waymo can't get guaranteed connection when it's out in the streets of San Francisco in a canyon. It's got to be able to do stuff on board. And then above that, decomposition into individual missions, and that's talking to the enterprise management system. In a warehouse, it's the WMS. For Waymo, it's where you, on your phone, say you want to ride, and it's got to then plan which Waymo is going to go where, who's going to pick you up. It's got to optimize all that. So you've got this stack, and then on the side, you have people acting in the environment, maybe deliberately interacting with the robot, and we see that in San Francisco with people giving shit to the Waymos, you know, going as though they're going to go off the curb. Let's see if the Waymo stops. Or as part of their work. And you saw the people interacting with the robot in that video. And then you get, so there's an interface there between people and robots that may be totally untrained people. They just have to deal with the robots in their environment. And then there's, you know, a web-based user interface for site managers. And then there's this whole other stuff on the left. There's a complete ontological mess of different methods. The geometric planners, so there's a geometrical representation of the world. There's a representation of certain knowledge, like in a warehouse. If there's a pallet on the ground, it's not going to go away by itself in 5 seconds. But if there's a person there, maybe they'll move away if I, the robot, move towards them. So the robot knows all sorts of stuff, but everyone builds a total mess there. So just like with LLMs, in this knowledge base, there's no distinction between what is true in general, what is true in specific about this warehouse, what is true in specific about today in San Francisco. It's all the same big mess of junky representations. We'll come back to that. There's a lot of room for improvement there. But there's a lot of stuff that's just gotten much better and is ready for prime time, like building vision-based maps automatically. We couldn't do that 3 years ago, just using vision. Now it just goes great. We've got a lot of AI running it. And so this is a warehouse. I'm going to use official US units. This warehouse is 4.5 football fields. That's the units everyone uses in the US for big, 4.5 football fields. And our robots map that. A single robot maps that in 3 hours, puts it up in the cloud. Now all the robots know where everything is. Those blue rectangles are shelf units. They're about 80 feet long, about 10 feet wide, and there's hundreds of them. But the robot knows where it is to within, mixed units now, to within 5 centimeters, 10 times a second. It references that map. We could not do that 3 years ago. Now that's available. It works well. And it's got a model of the whole environment. Another thing, say reactive navigation. It's matured well in the last 10 years. So here's inside one of our robots' brain. It's the white rectangle. In real life, we tell it where all the other robots are, the pink robots. We're going to switch that off for this demo. So the robots don't know where the others are, and they're all trying to get through. It's like a traffic jam, not knowing what's going on. And these robots are able to reactively see each other, see people, and get around without collisions. We run them for weeks at a time. A single collision, we would say, is a total disaster. Never collide. And here's another case. Just the robots pushing around. They don't know, oh, there's something in front of me. I've got to go around it. And then Manisha there, one of our engineers, she's going to skirt through. But just watch what happens here. She stopped. The robot stopped. They both reacted, but the robot was not going to hit her. So that's important to have that safety. And here's our chief counsel. He wants the robot safe. If you go near the robot, it just stops. So we use all sorts of things, AI up and down the stack, lots of AI, but it's not necessarily flashy new AI. There is some new AI, but there's also old AI. First one is control theory. That's not AI. But in the 60s, control theory was developed for robots in AI labs at Stanford and MIT. So it started out as AI. And I said earlier, you've got to be careful about introducing new stuff, new AI techniques onto robots. We use neural inference for image labeling. That first came out in 2012. It would not have been a smart move to put that on a robot right then, because we didn't know the limitations. We didn't know how safe we could make it. It took a while, 10 years or so, to really mature to a state where you can put it on a product and it makes sense. So I've had this long history in AI. And I've seen a few hype cycles in my time. Everyone thinks there's some hype now. There's been hype for 70 years. You can go back to the New York Times in 1956 and see hype about neural networks out of Cornell Aeronautics Lab. There has always been hype, and it goes around and around and around. Recently, I found this thing that I'd written, this stamp up the top that says 1988. It was the last page of a trade magazine. I said at the start, so this is 1988, 37 years ago I wrote this. That's what I look like, by the way, 37 years ago. Artificial intelligence has repeatedly inspired great expectations in people who see the possibilities of applying its technique. Sometimes it delivers, sometimes expectations are dashed. Here's another little highlight. Every so often, a new AI development comes along, and great excitement ensues as people stumble over themselves, convinced that the key to intelligence has been unlocked. Does that remind anyone of anything they've heard in the last year or two? It keeps going around and around. So I'm saying, calm down, people. There's great stuff happening, but it's going to take a while. And people who don't study history are doomed to repeat it. I'm the old guy there. Those who do study history are doomed to stand by helplessly while everyone else repeats it. And everyone's repeating it, guaranteed. And here's the mistake that newcomers to robotics make. I've heard that some robot startups, the 20-year-old dropouts come and say, and the good thing about us is we don't have any robotics engineers. We're not going to be tied by their mistakes. But they sort of make a fundamental mistake, thinking that robotics is about specifying motions for the robot and its components. But it's not. It's about deciding what forces to apply, when, and managing the total kinetic energy. So with our magic handlebar on our robot, which is measuring a force you're applying, when you push to make the robot go, if you're doing manual control, it accelerates at a certain amount. But if you're pulling back, it decelerates much faster, because that says you're about to hit something, and you got to pump that kinetic energy out as fast as you can. With wheels, yeah, you can manage the kinetic energy in the system. With a four-legged robot, you can manage the kinetic energy in the system. With a two-legged robot, it gets a lot trickier to manage the kinetic energy when it's falling. So robotics is gated by the physical contact with other stuff. It's not just thinking about things. It's not just generating words about what should happen. It's how the forces get applied. Progress is being made. So here's some capabilities that are coming along. The green ones, the left is a little cut off maybe, is engineering. You can do, an LM-based speech interaction with an indoor mobile platform. That's just engineering. You can do that. You can hire people to do that. You don't have to invent much. The next ones, some innovation is required. So human-safe four-legged walking platforms, as long as you're not behind them on the stairs as they go up, they're pretty safe. A little bit more innovation there. But in general, body reshaping to maintain stability when reaching and manipulating, we do this all the time. We counterbalance. Some innovation, but no real invention. The red stuff down below, whole arm and whole body manipulation. What do I mean by whole arm and whole body manipulation? When we're buying our groceries, we don't just pick the little thing up and put it like this. We do this, and we've got stuff under our arms. We've got something here. A waiter has stuff everywhere they're holding. Whole body manipulation. We do it all the time. Anything heavy, we use our body along with the arms. No one's doing that. Human-safe, adult-sized two-legged walking platforms. You're seeing a lot of two-legged walking platforms coming out of China that are about this high, and they're moderately safe. The trouble is, as you increase the size of the robot, the energy in it goes up by the cube. So if you make it 50% high, you see a little robot like this and it looks safe, add 50%, you just put 3.3 times as much energy into the system. And if that falls, there's kinetic energy that's going to go somewhere. Do not walk within 3 meters of a walking full-size humanoid robot at the moment. They are not safe. And most companies arrange so you can't get close to them. But remember that. And the bottom one, no way. Automated last 10 meters of delivery to consumers' homes. That is not going to happen anytime soon. And if you don't believe that, walk some of the hilly neighborhoods of San Francisco and see the houses. So the humanoid promise is that the robot's tall, get up, sensors are high, looks over human clutter, built for human environments, can navigate steps and stairs, change posture. The light blue, the companies are working on. The dark blue, walk like a person does, whole arm, whole body manipulation, not happening. And living humans, humanoids, also do a whole lot of other stuff, bracing against things, even with their fingers, touch the environment, letting people brace against them, all sorts of things. This is not happening at the moment. And I think the winners will be the ones who figure out the right data to collect and the right thing to learn for humanoid grasping. But I don't think anyone's got it yet. Now, you will see some videos of humanoid robots, and they pick up a bag and they, put it like this. What's real manipulation? If you're going to use robots to replace factory workers, what do you need to be able to do? I have 4 things in my pocket. One is a USB stick by itself. So I'll reach in there amongst the 4 and Oh, I'm not injuring myself, by the way. Notice that. And somewhere in here, I picked it's down at the bottom. Here it is. Here it is. Here's the. So I got that out, right? And now I'm going to get a bunch of stickies out. Now I'm going to get two things out at once. I'm going to get a earpod and a USB cable with a cable on it, and then I can manipulate them within a hand. And people in factories do this sort of dexterous stuff all the time. I'm going to show you a little bit of dexterity. The first part has some sound, then the last part doesn't. And I'm not saying that a humanoid robot needs to be able to do this, but it shows what humans are capable of. And then I show some food preparation with real humans, Julia Child from the French chef. So let's notice how many things I'm holding in one hand there. None of the videos of humanoids. Human hands are capable of this, applying those forces, incredible speed. And in each manufacturing task, they do stuff. Here's Julia Child chopping. And if you're working in a food preparation factory, you have to do stuff like this. And watch her grab everything. Two hands, scoops it all up. Doesn't pick up each little piece of slice by itself. Here's managing cutting fish. Very careful, you're feeling feedback. You've got all sorts of vibration sensors in your hand. You're using them all the time. And this sort of stuff has to happen in food prep, food processing. It's going to be hard to get humanoids to do that. So we got all this stuff, general architecture. There's a lot of room for improvement. There's improvement here in interacting with the world. There's improvement with this ontological mess, making that better. Improvement with interacting with people. The one place that things work really well right now are just this stack of planners. The planning has been around for a long time. There are open source optimizers. You can optimize the wazoo. And you'll hear LLM people say, no, we're going to make that better. We're going to put an LLM in there. No, not so much. Progress is being made, but it takes a lot longer than everyone expects to get deployment at scale. And I thank you for spending your time with me. Thank you.